Thank you very much to the organizers for giving me the opportunity to talk here. So today I want to talk about joint work with that goes back a little bit with Okado Shimozono and Fourier Shimozono on virtual crystals. And then we are going to apply this to some newer work in collaboration with Joseph Pape, Stefan Pfannerer, and Mary Claire Simon. And this work has just appeared in the Journal of Algebra. So let me start by giving you the motivation of what I want to talk about. So we are interested in invariant subspaces. So take, for example, the n-fold tensor product of some representations, v1 up to vn. And we want to know what is the dimension of this. And it is known that you can count the dimensions of this by the number of highest weight elements of weight 0 in some crystal corresponding to these representations. So if you have the representations v1 up to vn, you can look at the corresponding crystal bases, b1 up to bn, and then you can count these highest weight elements in there of weight 0, and that gives you the dimension of the invariant space. It's also known that the symmetric group Sn acts on v1 up to vn just by permuting tensor positions. And it was shown by Westbury in 2016 that the promotion action, which I will define later in the talk, actually gives the action of the long cycle on this invariant space. Okay, so basically the one that flips all the tensor factors. And what I will do at the end of the talk is I will show that if you take this invariant subspace, so basically you take as a set these highest weight elements of weight 0 in the crystal, you take the promotion action, which is some cyclic action, and then you take a particular polynomial in Q, which will be given by certain energy functions on these crystals, that this actually exhibits a cyclic sieving phenomenon. So that is sort of the outline of my talk. So let me begin by giving you some more details, filling in some of the details of how we can actually view these invariant subspaces using crystals. So here I have a very simple example. I'm looking at the crystal of type A1. So that just has one object, one letter 1 and one letter 2. And then the crystal is just a graph where the vertices are these two letters. And then you have an arrow between these two letters, which basically gives the lowering operator in the crystal, the F1 operator. And so what are the highest weight elements of weight 0 in an n-fold tensor product of this crystal? So weight 0 basically means that we have the same number of 1s and the same number of 2s. So for example, when n is equal to 4, we should have 2 2s and 2 1s. And then the crystal operators tell you that it's highest weight if we read from right to left, you always have weakly more 1s than 2s. So here I have listed for NS4 the two highest weight elements of weight 0, 2 2 1 1 and 2 1 2 1. And as you can see, as combinatorialists, they actually they correspond to Dick path of length 4 in this case, right? So you go 1 from the right would be up, up, and then the 2 is down, down. So you get up, up, down, down, and up, down. So you get the 2 Dick path. So those are nice combinatorial objects that we are all familiar with. Let me give you another example, a slightly more complicated example. So let's look at the invariant subspace for type CR. And again, I'm going to take an n-fold tensor product. So the crystal of type CR corresponding to a single box is just given up here. It's this graph. So the vertices are given by boxes filled with the numbers from 1 up to R and R bar to 1 bar. Okay, and then these arrows tell you what the crystal operators do. So this blue arrow labeled 1 tells you that F1 takes a 1 to a 2, F2 takes a 2 to a 3, and so on. That's what this crystal graph is telling us. And again, if we want to look at the invariant subspace, we now need to look at the elements of weight 0. So in this case, that means we want to have the same number of barred as unbarred letters, because they would add up to weight 0. And here I have listed them. So for n is 2, the only highest weight element of weight 0 would be this element from read from right to left, 1 bar. And for n is 4, we would have 1 2 2 bar 1 bar, and 1 1 1 bar 1 bar, and 1 1 bar 1 1 bar. So we have 3 for length 4. And you can also see that they are actually in bijection with what are called oscillating tableaux. So if you start with weight 0, so I denoted this by empty, and then you just go tensor factor by tensor factor and you look what the weight is. So for example, let's look at this case. I start with empty, then I add a box of weight 1, so I have a single box, and then I again, the bar means I remove a box of weight 1. So then I end up at empty. And you can see that all of these actually correspond to oscillating tableau, where you can either add a box or remove a box from your partitions. Okay, so that is another example. And let me give you one last third example, which corresponds to the spin representation for type BR. So here I've given you the crystal, the spin crystal for type B2, and we will look at more general spin crystals in a moment. But in this case, the elements are just tuples, in this case, 2 tuples of just pluses and minuses. And the 2 crystal operator just makes a top plus into a minus, and then the 1 operator just flips the plus and minus. And here I've again listed all the weight 0 highest weight elements for a tensor product of length 2 and 4. So these are those. And you can see that these are actually a natural bijection with, in this case, 2 fans of dick path. So in the case of BR, these would be R fans of dick path. And the way we can see this correspondence is, so if you think of the bottom row here as my white path and the top row as my green path, then a plus would go up, a minus would go down, and you can see that we have these fans of dick path corresponding to these tuples of pluses and minuses. So this is to say that these invariant subspaces are actually labeled by very nice combinatorial objects. So what I want to do is I want to now study these, and they are known for certain types, and the types that we are interested in, we can actually study by using what are called virtual crystals. So I briefly need to tell you what virtual crystals are. So suppose you have 2 algebras, X and Y. So on this slide, I've shown you where X is type CR and Y is type A2R minus 1. So I've drawn these 2 dinking diagrams for you. And so suppose we have some embedding of these algebras. So in this case, we are embedding type CR into type A2R minus 1. And we do that by folding the type A dinking diagram. So you can see that I've sort of drawn this type A dinking diagram folded. And to define the virtual crystals, the functions that are actually important for us are the sigma. So the sigma just tells me which nodes in the Y algebra are sort of folded together to give me a node in the type X algebra. So here in this example, you can see that the nodes I and 2R minus I are sort of folded together to give us the node I for type CR. And then the rth node is actually just a singleton. So sigma of r in this case is just r. And the other data that we need are these multiplicity factors, which I call gamma I. So every node also has a multiplicity factor attached to it. So the multiplicity factor for I between 1 and r is 1. And then this last node, the rth node, has multiplicity factor 2. And then we can embed the roots and the weight lattice of the type X algebra into the type Y algebra by mapping a fundamental weight Wi for the X algebra into a sum of weights of the Y algebra. So you can see that this multiplicity factor here appears, and we are also adding things that that associate under the sigma map. So a virtual crystal is now a realization of the type X crystal in terms of a type Y crystal. So I'm going to call the type Y crystal, I'm denoting it by hats. So that will be my ambient crystal, and the associated crystal raising and lowering operator will also be denoted by hats. And the virtual crystal operators, the ones that will sort of model the type X crystal, are given by products of the type Y crystal elements. So for example, EI will be a product of things that are associated under this folding, under the sigma, and with this multiplicity factor. Okay, and then a virtual crystal is just a subset of our ambient crystal, such that what you need is that the string length, so these epsilon I and phi I just denote how long a particular string of labeled I is or J is. So we need that they behave well with respect to this map sigma, and they also all need to be multiplicities of this multiplicity factor. And we also need that the subset that we are choosing is closed under the virtual crystal operators. And if that is the case, then it is known that if you take two virtual crystals and you take the tensor product, this will be, again, a virtual crystal inside the tensor product of the ambient crystals. Okay, so this is sort of some theoretical background that I will need. And now let us apply this in the setting that we are interested in. So remember, one of the examples I had were these spin crystals, and we are now going to model them by some virtual crystal embedding. So here I have drawn the spin crystal of type B3 for you. You can see that F3 makes just a plus into a minus. And then as before, an Fi operator sort of interchanges a plus minus into a minus plus. So this is the graph of our spin crystal. And we are now going to model it using a tensor product of type C3 crystals, where we map this plus 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 to the highest weight vector 3 to 1, and the crystal operator F1 over here in the spin crystal is modeled by the square of F1 operators in the virtual crystal. And similarly, the F2 is a square, but the F3 is just the F3 operator. Okay, so the 2, 1, 1 in this case will be our multiplicity factors from before. So the takeaway from this is that we can model the B spin crystals as basically as type C crystals. Okay, so now the other object that I promised you was this promotion operator. And the promotion operator can be defined in terms of what is called the crystal commuter. This was introduced by Enriquez and Chemnitzer. And what this commuter does, it takes the tensor product of two crystals and it wants to basically switch them. So B lambda, B mu, you want to map it to B mu, B lambda. And the way that this is defined is by using the Lustig involution. The Lustig involution is basically an involution that takes your crystal and turns it upside down. It maps the highest weight vector to the lowest weight vector, and it flips the raising operators to lowering operators. Okay, so in the examples that we are interested in, it will actually just map an Fi to an Ei. But in type A, it would map an Fi to an E2R minus I. ER minus I. Okay, and so this was the commuter. Now to define the promotion operator on our crystals is, remember, we are basically looking at n-fold tensor products of crystals. And what we do is we sort of split off the last tensor factor and move it to the end. And you can sort of see that this would correspond to some cyclic action on the tensor factors where you move one tensor factor and you move it to the end, right? This corresponds to a cyclic action. And we do that using this crystal commuter. So here's an example. Let's take 2, 2, 1, 1 in the four-fold tensor product of the single box crystal, which we saw before, is actually labels one of these invariant vectors. And so what we do is we split our four-fold tensor factor into a three-fold tensor factor, and then just a B single box. And then we are going to move the 1 basically to the end, but using this crystal commuter. So we have to compute the Lustig involution and then move things to the end. And what comes out is the 2, 1, 2, 1. Okay, so that is, but you can define this like in general for any sort of crystal, not just for the simple example. And what we are now interested in is basically a map that maps these objects in this invariant subspace to what are called chord diagrams. And here I've drawn you an example of sort of what we are interested in. So for example, here in blue, I have drawn for you the crystal elements that correspond to this invariant subspace. So remember, those are words of a particular even length where we have the same number of 1s and 2s, and such that read from right to left, you always have weakly more 1s and 2s. These are in bijection with standard Young tableau. And the way that this bijection goes is just if you label things from right to left, then if you see a 1, the letter in that position is in the bottom row of your standard tableau. So for example, here we have a 1, so you have a 1 in row 1, then we get a 2, so you have a 2 in row 2, and so on and so on. And the promotion I just defined you corresponds on the standard Young tableau just to the usual promotion operator on standard Young tableau, where you remove the 1, you do jeu de taquin, you subtract 1 from every letter, and you fill in the empty box. Okay. But now what we want to do is we want to map this to chord diagrams. So the chord diagrams I have drawn for you down here. So in particular, 1, 2, 1, 2, 1, 2 corresponds to this chord diagram where we connect 1 and 2, 3 and 4, 5 and 6. And the promotion operator just corresponds to rotation of this chord diagram. And you can see that this is true also in all the cases, right? So here on the right, I have another example where I have a promotion orbit of size 3. And you can see on the level of chord diagrams, this really corresponds to rotation of my chord diagrams. And I should say that Stefan Pfannerer is giving a talk right after me. So he will talk in more detail about generalizations of this. Okay, so basically what we are after is some map, which I called CD, from these weight 0 highest weight crystal elements to chord diagrams such that it intertwines promotion and rotation. And this was already done for type A and C by Pfannerer, Ruby, and Westbury, using work by Peterson, Piljavsky, Rhodes, Patrias, based on work by Cooperberg. And what I'm going to do in this talk is to do this for type BN. And I hope you can sort of see now why these virtual crystals come in handy, because we can now embed BN into type CN, and Pfannerer, Ruby, and Westbury have already proven things for type CN. Okay. And so the way that this works, how this construction actually works, since I've only a half an hour talk, I can't talk about this in great detail, but here's sort of an outline. So we define this map from the invariant subspace to the chord diagrams in two ways. One is using certain fillings of promotion evacuation diagrams introduced by Christian Lennart. And this way of viewing things shows that promotion and rotation actually intertwine. And then the second way is using foamine growth diagrams. And this way of viewing things proves injectivity. And we do all of this, as I said, using virtual crystals. So let me just, since this was a little bit fast, let me just do this in terms of one example, but I refer you to the actual paper for more details. So here is one particular element in the invariant crystal, so a highest weight vector of weight 0 in type B3. So what we do in this sort of table is, first you write down the weights of this, you going from right to left, right? You start with weight 0, 0, 0, then adding the plus, plus, plus gives us weight 1, 1, 1, and so on and so on. So that gives us the first row. Then you compute the promotion orbit, and you keep writing down what these weights are, so you get this particular diagram. And then what you do is sort of you cut this diagram along this line, and you make it into a square diagram. And again, I refer you back to the paper for details. And then what you do is you use a particular map which adds things on the diagonal plus things on the things on the diagonal minus things in the corner, and then you count how many negative signs you have, and that gives you this particular matrix. Okay, so now these numbers appear, and that gives us a matrix, and then you view this matrix as the adjacency matrix of your chord diagram. So that was sort of like a crash course in how you can go from these highest weight elements to a chord diagram. Okay, so in the last 5 minutes of my talk, I briefly want to tell you about how we can use this to define a cyclic sieving phenomenon. So the cyclic sieving phenomenon is a generalization of the Q equal -1 phenomenon introduced by Stembridge. And what you need for this is a finite set X. Then you need a cyclic group acting on the set X. And you need a polynomial. Here I'm using a polynomial in the variable Q. And then you say that this triple of the set, the cyclic action, and the polynomial, this exhibits a cyclic sieving phenomenon if the fixed point, the number of fixed points under this cyclic action is equal to the polynomial evaluated at roots of unity. Okay, so what I'm going to do now is I'm going to present to you a cyclic sieving phenomenon for these objects that we discussed. where the sets are basically these combinatorial sets that describe the invariant subspaces, and the action, the cyclic action, will be the promotion action that I introduced for you. And the polynomial will be some polynomial that uses the energy function. So let me briefly define for you what the energy function is. So basically, the energy function is something that comes from statistical mechanics, and this actually uses affine crystals. So you also need some zero action on your crystal. And the local energy basically is defined by recursively by saying you add plus or minus 1 or nothing, depending on how this affine crystal acts. So the details are not that important, because I'm actually going to give this to you explicitly in the examples that we need. So for type CR, this is my affine crystal, and you can see that the local energy function is basically just looks at descents. So if I use this ordering of my letters, then the local energy function is 0 if everything is nicely ordered, but if you see a descent, it is equal to 1. And similarly for the spin crystal, there's an explicit formula for this local energy function in terms of the number of minus signs. And then the total energy function is some sort of generalization of the major index, where we sum up these local energy functions, but weighted with this number I. So this is really some analog of the major index. And then my polynomial is basically the sum of Q to the energy function. And then what we proved in our paper is that if you take X to be this set of crystal elements that label the invariant subspace, you take the promotion action as your cyclic action, and then you take this energy function polynomial. This actually exhibits a cyclic sieving phenomenon. And the proof really relies on work of Fontaine, Chemnitzer, Fourier-Littelmann, Fourier, myself, and Shimozono, and a paper by Westbury. Okay, and then in the very last minute of my talk, I want to end with one conjecture, namely that we actually conjecture that there's another polynomial that you could use for type BR, which is given by these sort of Q deformations of quotients of numbers. And these numbers actually count the number of R-fans of Dick path, and we conjecture that this actually also gives a cyclic sieving phenomenon for the same set. And this was also previously conjectured by Sam Hopkins. And here's an example to show to you that this is actually non-trivial. Here is our polynomial on the top, and then the G polynomial in the bottom, and you can see that they're not the same, right? This polynomial has Q to the 12, whereas ours does not. But modulo Q to the 6 minus 1, they're actually the same polynomials, and therefore they actually give the same cyclic sieving phenomenon. Thank you very much for your attention.